Assalamu alaikum dear students, we're back with another video lesson. In the previous video lesson, we were talking about Lenz's law mostly. We said Lenz's law says that the magnetic field of the induced current is in a direction opposite to the change that created this one. Magnetic field it will oppose the magnetic field that induces this one, which is mostly, we said that it is from a bar magnet. Alright, and we also learned about a lot of things regarding Lenz's law. Lenz's law, it is used to tell or determine the direction of a current. It doesn't tell us any information about the magnitude of the current that is induced or the EMF basha. It can only be used to tell the direction. Lenz's law illustrates the law of conservation of energy. Lenz's law, and according to the Lenz's law, the EMF this induced magnetic field always tried to keep the total the same constant basha. And so this is what you need to know. Also, if the magnet, if they're getting closer to one another, they will always have the same pole, north or south, it doesn't matter. But if it is moving away, they will have opposite poles, bashkaka. And then this is where we stop right at this point here, it needs a little bit of time. This is why we did not do this the previous lesson. An electromagnet is placed next to a coil of wire. Electromagnet chapter 5 when a current passes through a coil of wire or solenoid, there will be a magnetic field around it, as you can see from this one right here. In the arrangement shown below here, according to the Lenz's law, what will be the direction of the induced current in the resistor R, because this is where we want to find the direction of the current here, in the following cases. Part A says the magnetic field suddenly decreases after the switch is opened here. There are a few things I need you to know here, first of all. What we have, right? We have an electromagnet, like we said, chapter 5. So here's how the coil is wound, you could say, around this one. Let's use this color. So this is, we can say, how the wire is wound around the coil here. So we have an electromagnet, one side positive, negative here. So this is a battery, we can say, and there is also a switch. Let's just draw the switch in here. So we consider that we're going to close the switch. There is, we can say, an electro coil with a galvanometer here. This not a galvanometer, we have a resistor here. So we're trying to find the direction of a current in this resistor. This resistor has right side and left side. So we're going to see if the current is going from this side left to right or right to left. It comes out, let's say, if the direction it says if the magnetic field suddenly decreases, what exactly this mean here? And magnetic field decrease what exactly, or how does that induce EMF later? Before we do this, there is an arrow as well here. This arrow would also tells you the direction of a magnetic field, but ignore that arrow here. Chapter 5 this is chapter 5, you could say, and this is chapter 6 here. Chapter 5, if a current passes through a current, there will be a magnetic field around this one. We know that the direction of the current, you've learned that it is always from what? From positive to negative. According to this, is that we can tell which side is north or becomes north and which side is south. Where this is how the current is flowing through the circuit. This is how it is going. It is going to move behind the coil here, then it goes back in here, there, and then here. This is how it goes. That is if we close the switch, So this is how it goes normally, As you can see, it is always going from north to south, from positive to negative, it must be moving towards the negative side here. This is how it is going. If that is how the direction of the current is going, according to the right hand rule, the vichan positive, vichan north, vichan south, this is the direction of current now. The direction of current, it is opposite to this, or you can say this is how it is. You can see that this side it must be north, to south, right? This is, or knowing this is very important. This is north and this is south. Why is it important? Because based on this, we know that again, If this is getting closer, they will have the same pole. If this is moving away, they will have opposite pole. When you kata, this is crucial. أو زوجو gringa bzani chan north or south. Where you can say, Baba, isn't this exactly the same as a bar magnet now? Exactly the same, Basha. But chapter 5, I got Levi Baba. And this is the same as we can say a bar magnet now, north and south. When you direction magnetic field will always go from north to south, and that's it. Basha, yalla dema ishman bo magnetic field needs if we go back to the question, if the magnetic field suddenly decreases, if we go back to this, the magnetic field suddenly decreases after the switch is opened. Basha, if we open the switch, let's go back to this one here. So now here's, I believe I should write this one a little bit higher maybe. But before that, there will be a magnetic field around this. Let me draw this one too. The direction of a magnetic field that is always from north to south. Again, if we open the switch now, what do you think will happen to the magnetic field line? Does it increase or decrease? Now, switch open. Now you can see that the magnetic field around the coil start to decrease or disappear. As you can see here, my magnetic field line can come because you open the switch, there's no more current flowing. Magnetic field line can isn't this the same effect as if we move the north away from this coil here? Or imagine we had a magnet and a coil here. Magnetic field line when the magnetic field line is decreasing, isn't that the same effect as if we move the magnet away from a coil? If it is now, it is the same effect as the magnet moving away. It's a magnetic field because the switch is open. Because it is starting to decrease. But think about it in slow motion, because this happened in a fraction of a second. When the switch is off, immediately the magnetic field is going to disappear or kind of like fades away. But if you just use that, for example, if you use a slow motion camera, you can see that the field is slowly decreases until it becomes zero. Slowly decreasing, it is the same effect as if this magnet or this coil is moving away. North B. And if it is moving away, the other side here, will it be south or north? If it is moving away, they will have opposite poles. South. South north. Is that in this coil like it is any man shad? Because obviously there is a change in a flux. Can I tell the direction of a current or not? Yes. Man, if I do this, that would be wrong, Kaka. Man, this is what we do, because it is the same effect as moving away. The beta north the beta south, direction current it is pointing downward. If it is pointing downward, watch this, If it is pointing downward, obviously, I should just follow the arrows here. It is going from left to right. This is how it is passing and going through the resistor, and then after that it keeps moving through the circuit. This will be the direction of a current if the switch is opened. It is going to go from left to right from the resistor. That is the first part of the question here, where you can say part A. That is part A. What about part B? What is part B saying here? Part B says what? Part B says if the coil is moved closer to the electromagnet. Now consider, of course, we have the coil is connected, so there is a magnetic field here. So let's go back or maybe copy paste this. So this is the electromagnet. I should have done with the coil too, but that is okay. And here's the electromagnet. The current is flowing through the circuit, clearly. One side is north, the other side is south. And here's the coil now, This is the resistor. This time, this is the coil. If the coil is moved closer, if they're moving closer, they will have the same pole and opposite pole, the same pole. north beta north the beta south. north beta south direction current use the right hand rule here. Gutman, your thumb must point north. Direction كرنت كي وزارة لو سري دبي باشا. This is how it goes. You could just follow the line here. Okay, remember this was the right side. This was the resistor. This is the left side one, yeah. Right, left, yeah. Got that. This time it is going from right to left one, yeah. This is how it goes. Got the direction on the resistor is going to be from right to left side. This is how it continue. Bashkaka. That's a decree, of course. They could change this one here. They could change the polarity of this positive negative sign here. And then, of course, different things could be done with this ball cushion too. Basha. So in this case, of course, it is going to move from right to left, as you can see here, Baba. Malera, switch open boom magnetic field slowly decrease the biocat is the same effect as saying a bar magnet and Baba and the magnet moving away. Let's see why is not writing. No, it's because of the other one, or what is but it is the same effect as this magnet moving away. Good man, if it is the two are moving away, they will have opposite pole. Later north, later the beta south, and the beta north. Use the right hand rule. Your thumb must be pointing north. Kata direction current. If you keep following, one direction current it will be from left to the right on the resistor here. But for the second part, good man, if the coil is moving closer, once they're moving closer, they will have the same poles. Of course, now the switch must be closed at that magnetic field. Come on, habitin, so that we have everything there. These two will be the same. Your thumb must be pointing the north. Direction this time it is going from right to left on the resistor. Practice it is very close to that one. Let's solve this one too. The bar magnet is positioned near the coil of R shown in the figure. What is the direction of the current in the resistor R later when the magnet is moved to the left? If the magnet is moved to the left, or right side or left side, if the magnet is moved closer, if they're moving closer, they will have the same pole. Like south, south tabi kata like edi ka north be use the right hand rule baba kata tabi direction current up beaten. This is how it goes. Kata data era from this resistor here. This is how it is going. When kata it is going from right to left. Go right to left resistor. Which one is correct? From left to right, from right to left. That'll be the correct one here. In the in two opposite direction, all of the answers are wrong. Now kata only option B would be correct. As you can see, baba. It is repeated many times. The created polarity can. These are copy paste, by the way. With the creation shileb gore asaya, whichever or whatever that you do, that'll be totally fine. But later, you can see that. What does it say? It says the coil is moved closer of the electromagnet. What will be the direction of the current in the resistor? Let's say. When will the direction of a current in the resistor will be from right to left? Let's get that shababa. Liberate option A you see there. حزم له وتماشاش كان بزام داخوا أو option A you see راستيان زيادة وهيتي تدانة. An electromagnet is placed next to a coil of wire shown here. According to the Lenz's law, in which of the following direction, Basha, is the direction of the induced current in the resistor is from left to right. Now, let's case such a direction from left to right. This is right, Basha, and this is left. And let's case such a direction to left to right, Basha. But it comes out that when the electromagnet is moved away from the coil, when the electromagnet, if it is moved away, then the bibzanum channel north and south, so that we can tell if it is the same pole or opposite pole. When later north, direction current goes from positive to negative, it goes behind the coil and then comes back. This is how it comes back here. If that is the case, kubzam channel north and south. Again, because it is pointing downward, this side is north, Basha. And you can also tell by this direction here as well, Basha Kaka. Era north, era the beta south, Basha. And if the electromagnet is moved away, if it is moved away, Kaka, era the beta south, era the beta north, Basha Kaka. Okati direction, you can see that. Align your thumb, point your thumb to the north, and direction, this is from left to right. Rasta, Basha. What about when the electromagnet is moved closer to the coil? If it is moved closer to the coil, أوقات يعكس دبيته. كاتا is going to be قلت معنا قال لي north be if it is moved closer ليش دبيته north دوباره باشا كاتا أوقات يشتكى عكس دبيته this is how it is going ونيا كاتا دبيته right to left أو غلط دبي كاتا not be ونيا أدي سيتي بابا تلا when the magnetic field suddenly decreases after the switch is open أو شنو ما نقول عين effect بابا أجر if the switch is opened كاكا يعني اللي رجعبك دبي أو magnetic field ده كوا that is around the coil it is suddenly decreasing بابا قلت ما magnetic field ده decrease دبي it is the same effect as if you move the coil away man if that is the case ليرة دبوا north ليرة north وطبعا ليرة south it is if the magnetic field is decreasing قلت ما وكوي as if you move the electromagnet away ليرة north ليرة دبي to south ليرة south بي north or south كاتي تيلي دي باب direction كا قلت man bono عيلي ديتن and that is also going to be from left to right كاتا ليرة هردو option راز دبيتن option A option C which in this case we're going to choose option D because this is both A and C هواي دي كده تسدل بابا زمانا أسانا rapidly inserting the north pole of a bar magnet into a coil connected to a galvanometer the needle of the galvanometer deflects to the right what must be done to deflect the needle of the galvanometer باشا to the left قلت ما انت مع شباب لو حالة انت ناخذ diagram ماشي دروب if the north pole here's north pole this is south if it is entered into a coil of wire here عشان ليرة بخوي بيدلا بسالك the galvanometer needle is shifting to the right أو بخوي بيدلا كاك ضليت سبكن أتا needle كا أو زاري shift كاتن to the left باشا if this is north pole باشا the north pole باشا says it is rapidly inserted into the coil باشا كاتا pull the north pole of a magnet out of the coil that's that if you pull it for example pull away if you move the magnet away أو كاتي this galvanometer needle it is going to shift to the left ونيا كاتا this is A is correct let the magnet set at rest no EMF will be induced thrust the south pole of a magnet into the coil أو زاري قلت ما أنا north يبيني باشا it goes to the right what if you move south into the coil أوقات of course is going to be opposite which is going to shift to the left again because again north beat the to right كاتا south beat and the to left كاتا in this case we can say both A and C are again correct again لو خالبي وشو أبزمنا نسلايا the light determines which of the following the magnitude of the induced current magnitude of the induced EMF direction of the induced current and all of them C will be correct now Lenz's law can be used to tell what is wrong with this Lenz's law can be used to tell the direction of the current only أقل ليبي قلت ما magnitude اشتكان علاقة لنزيني علاقة شوية علاقة فاراداي okay باشا what is Faraday بابا man is that Faraday man is obviously the scientist who found the relation between the induced EMF and also we can say the change in a magnetic flux what did he say basha so we can say Faraday's law of electromagnetic induction predicts the magnitude of the induced EMF كاتا شيء magnitude أو EMF there's the be in this process would tell us Faraday did basha so we can say that to calculate the magnitude basha of the EMF induced يعني induced EMF basha you must use Faraday's law of electromagnetic induction what did exactly Faraday said that baba he said that the EMF induced EMF بس معناه بابلن voltage يعني potential difference it is induced basha he said that or he stated that he said that this EMF that is induced it is directly proportional to the rate of change of flux we've learned that whenever something says or it says the rate of يعني something divided by the time the rate of what the rate of change in flux يعني when the flux changes over time that change induces EMF basha in that coil or circuit bubbling circuit basha alright so كاتا the line Faraday's law baba of electromagnetic induction states that the electromotive force or EMF basha induced in a closed circuit basha it is directly proportional to the rate of change of magnetic flux through that circuit here so as an equation here how do we I'll write that as an equation, Baba. We can say Faraday's law of electromagnetic induction. So we can say EMF, this stands for the voltage that is induced. Basha. This stands for the voltage that is induced. It is directly proportional to the rate of change. Rate yani something divided by time. Change of what? Change of magnetic flux. But if you want to change that into an equation, we'll say EMF that is equal to, Basha, whenever you change a relation to equation, you have to add a constant. So that is going to be m times, that will be the constant, times the change in flux over time here, Baba. That is this. But there is also a negative sign here, don't forget. Basha, Kata, this is now, we can say this is Faraday's law of electromagnetic induction, which tells us how much or the magnitude of EMF that is induced. Bash Kaka? For example, what if you want to know how much current is induced? We have Ohm's law, resistance, EMF lesser current. Now, if you want to know how much current is induced, then you will just cross multiply, then current induced, the EMF that is induced, divide by the resistance of the circuit, the coil, whatever, then you can find the induced EMF. Basha? For the induced current. Let's go with man. Current, of course, if we have a closed loop, then there will be a current induced as well. That is how much current will be induced. So let's go back to this equation right here. Now this EMF that is measured in volt, you can see that this is N. What does this N stands for, Baba? That is the number of turns for coil or for solenoid, whatever. This flux here, or change in flux, you know that. This change in flux, which is measured in what? Measured in Weber here. Let's just say WB here. What about this delta T, Baba? That is the time, which is measured in what? Measured in second. You might say, what about this negative? What does this negative indicate and represent? This negative represents that the direction of this induced EMF will always be in a way such that it opposes the change that created this, which is stated by Lenz's law. Lenz will always be in a direction such that it opposes the change that made it. But you know that magnetic flux magnetic flux. If I just rewrite this one here, before we've learned that magnetic flux AB cosine theta. Can we substitute this into that equation? Yes. The 20 blend EMF induced. The negative N. Changing, because there is a change. If there's no change, there's no EMF. So the AB cosine theta divided by Ch divided by delta T, Baba. Now, regarding the units, there's something very important I need to know. I need you to know. We can write two things. Let me write the other one as well. Change in flux over delta time here. Later, Baba. If I want to find this one here, the chapter 5 Gutman flux the Weber of volt times second. I'll tell you where it comes from now. Later, this is volt, measured in volt. This is number of turn, has no unit, Basha. Later, flux it is measured in Weber. Measured in second. If you cross multiply here, Weber it's later, Baba. Weber volt second Now, if we go back to this side here, the 20 blend, volt Baba if I want to do it here, for example, volt, Gutman A, that is meter squared. Number of turn has no unit. Magnetic field measured in Tesla, cosine no unit, second. Volt meter squared times Tesla divided by second. Whether 20 لجاتي second because the second you could write it this way here. Time is 1 over second. 1 over second is the 20 وكهرتز بينوسي. زورا سايشتو أبيتو. Let's write the 1 over second again. What if I want to make the B as the subject or Tesla as the subject? Tesla is subject the beta volt times second lesser matidusa. These are something very important. I need you to be aware of these units because they've been in Wizari Kaka. Of course, now this second, what is it called? You can bring it or take it to the bottom here. That'll be volt over meter squared times hertz as well. There's one more thing I need you to know, Baba. Later, Catalan change. Basha, obviously or clearly, one of these will change. Basha. So whatever that is changing, you can keep that over the time. Like you will see that in a lot of questions later, Basha. For example, if the magnetic field is changing, most of the question, the magnetic field is changing or be here. So we can say the EMF induced here, the negative N, those that doesn't change, you could just extract them or bring them out of the bracket here. So times A cosine theta, if these are not changing, if the magnetic field is changing, that would be changing magnetic field over time. And changing magnetic field, you could always say that B2 minus B1. B final minus B initial over the time. I got area change ka baba. Okay, we'll write the B here. Basha. In this case, we'll say area 2 minus area 1. Basha. And then that'll be it. Basha. And then we have questions where the magnetic field is changing or the area is changing. It is one of the two here. Basha. These are, I can tell you that all of the EMF that is induced by, or you can say Faraday's law. So now we can, and by the way, this is, we can say for a coil. Bashkaka. For what? For a coil. So if I ask you a question, what does the strength of the EMF induced in a coil depends on? Depends on the number of turns, depends on, let's just rewrite the equation here. EMF got mine in a coil, like I'll leave it the negative N, Basha, got mine A cosine theta. Let's just write the whole thing here. Changing AB cosine theta divided by delta T kata. The EMF induced in a coil depends on a few things, Baba. The first one, the number of turns, which you can see that is directly proportional. Number two, the cross-sectional area, again, directly proportional. Number three, the magnetic field strength, directly proportional. By the way, when we say B cosine theta, that is the whole thing you can say. These are all considered as one factor, because that will be the component of a magnetic field that is perpendicular to the cross-sectional area. I'll explain what this means in a second. And then the fourth one here, that'll be the time for the change, whatever the changes, whether it is the magnetic field down the area, but these are inversely proportional. I got leave. أو B cosine theta ما بس تيجي بابا ما بشتري باسي flux marker بتمان أجل ليرة magnetic field دكا perpendicular بو magnetic field دكا أو كاتي we can say change in magnetic flux دكاتة دكاتة AB cosine theta when OB cosine theta بابا represents the component that is perpendicular to the surface and they get perpendicular نبو. For example, like we said, this is the normal to the area magnetic field دكا بابا bono عيبو. Okay, then this one obviously becomes two component. And yeah, we will get two component. Yakachan the beta. It's supposed to be this. Got my data. Yakachan the beta B cosine, or the beta B sine. And yeah, so which one of them is perpendicular to the cross-sectional area? It is this one. And when yeah, got my humza the magnetic field. The perpendicular be okati, bazagali perpendicular bu. The angle between B and N becomes 0, then cosine 0, and B cosine 0 represents the perpendicular component that produces EMF. It's got the parallel, and if it is parallel, there is no magnetic flux at this point here. You can rewrite if the cross-sectional area is written like this. You could say, for example, this is the perpendicular component, magnetic field, then this side here becomes B cosine theta, which is the perpendicular component for magnetic field. So the create do component, if this is the direction, right? So it could be either this or that. This is parallel to the surface, you can see that. So this one produced no EMF. This perpendicular component produced EMF. I hope you understood. I can ask that you right to that. So this is the EMF bubbling of the induced, and bubbling the EMF induced, which is stated by Faraday law. Kata Faraday, what is Faraday law, Baba? Tigo. Kati the electromotive force induced in a closed circuit is directly proportional to the rate of change of flux, or magnetic flux through the circuit. Gutman equation naka EMF dakata tibaba, dakata electromotive force dakata negative and change in flux over delta time. I got Levy flux dakata AB cosine theta l then we'll get this equation. Basha. Kata magnetic flux depend dakata ushtana. That is not important because you've studied that before. On a few notes and study tips regarding the equation, this negative sign indicates that the induced magnetic field opposes the change in the applied magnetic field as stated by Lenz's law. But man, this term B cosine theta represents the perpendicular and the component of the magnetic field that is perpendicular to the plane of the loop. هم زائد ده magnetic field دكا perpendicular be to the plane of the loop. أديك perpendicular نبو angle ما نحبو try to make that as a component or component perpendicular. Choose that one. Yeah, the angle theta is measured between what? The applied field and the normal to probably normal to the area and to the plane of the loop. As indicated in this figure, and I believe that's it. You know that in chapter 6, knowing the unit and also subunits, their equivalents are very important. It comes out of Zana, SI unit and also what do they equal to? For example, you know that the unit for magnetic field is Tesla, or SI unit but Tesla dekata komalak unity dk, so you need to know them all. So how do we get this correct, or like for example you get the hang of it باشا بابا هم زارب زانا وكستدي تبك زوزو راسان بداية man, whenever you're given a unit kaka whether if it is this or that kaka هم زارب زانا أجري نيتي دابو بابا that means this is a force Again, force we only studied magnetic force in chapter 5. That equation belongs to chapter 5. So think about an equation that has force in it, or Newton, let's say force in it in chapter 5, and make sure that you get into this one here. Again, Newton volt baba. Volt volt, it comes from EMF. EMF chapter 6 this equation must belong to chapter 6. If you know which equation, or like this equation belongs to which chapter, of course it makes it way easier, kaka. Then of course I'm sure you can find your way out. For example, Tesla Weber I think that's the most obvious one. Hamu equation ana bumsaka magnetic field magnetic field strength starting from the first one, because we have Weber or magnetic flux it comes from this equation unit كان ناخذ بك equation Weber each magnetic flux meter دزاي area اوش Tesla دبيت magnetic field كاتا محالوك cross multiply we can say that flux دكاتا B times area باشا equation E magnetic flux كاتا this is easy when you Tesla دكاتا on and you can see that it's written over there. أدي لي بابا Tesla دكاتا Newton second coulometer ما دام Newton بابا قلت man that must be belonging to chapter 5 دير قلت مال لذاتي وانا اللي خد بيك equation او نيوتن unity بابلن فورسيا second unity time باشا or delta T coulomb is a unit of charge, meter is, we can say it is a unit of what? Unit of distance unity distancy let's just say distance كاك or delta x يكشتي باب اللي ربزانا قلت معنا وش obviously it is a bablin, it is a magnetic field because it is Tesla باشا ماشا زارو بار اللي خد بزانا باب is that think about an equation that has force in it on chapter 5 هشا ما دام distance time تدا يا بابا distance كي and time كي بينا بين distance كي او the beta velocity أجر وش نزاني think about an equation that has in chapter 5 that has force in it one of the equation that we have بابا it is magnetic force دكاتا Q V B sine قوش ليرة sine وما كان ور مغرب بابا ما ليرة نيوتن ليرة كولوم ما ليرة meter per second كاتا this must be from velocity and this is Tesla كاتا this is what it is. So Tesla equal to is the meter per second then bablan second daka. It can be going to the side of the Newton, then you will get this one. This is how you can easily get it. There baba. Tesla daka Newton. Madam Newton this must be chapter 5. Think about an equation and you can see over there. There, this one is a bit different here. Tesla volt second لسر meter دزا baba. There volt يعني EMF chapter 6 قال لي the chapter 5 we don't have EMF induced basha. Man, this is a second, so obviously time, and this is meter squared, which is area, this is B. You can cross multiply this, see if you can get to somewhere. Kata billion EMF times delta T, the kata B times area. This one, if you take this time under, right, what do you get? EMF the kata babylon A, B over T. This one is Faraday's law. Kata lera number return here, which because it has no unit, we didn't write it. There's a negative there. There's AB cosine theta, which we don't write the cosine over time kata. This is also right. This is how you can get to the bottom of this one without making any mistake. And of course, you could do the same with any other units, Baba. It's totally fine. It is a very effective method. رأيك زور آسان وزور باششة so that you could do anything that you want. باش عندك بساري وزارية نخد حاليا كباش بابا. أو بساري كان رنگ بونو أي بيتو يعنيش بونو أي تزانم بونو أي جواز يعنيش بونو أي لديتو بابا. It doesn't matter if they say for example volt second per meter as a whole word يعنيش تتواني بس symbol بدني يتشو شكل نابي. أو أنا شو بزانم زور آسانة ونيا لو خد عندك practice كو والله ما كان ببينه. Which I would rather you give it a try. But actually, come on, Baba, what four factors affect the magnitude of the induced EMF in a coil of wire? Basha, good man, four factors that affect the bubbling induced EMF in a coil like a lebi Baba. Man, madam dala in a coil of Faraday like what I equation kebinus a negative n, good man, changing A, B, cosine theta divided by delta t. Kata yak 2, 3, Manohami is one factor, and this is going to be the fourth factor. Got that? The number of turns, the area, cross-sectional area in bubbling, the component of the magnetic field that is perpendicular to the area, and also the time taken, let's say, for the change, or just the time taken for this to be happen. If you have a fixed wire or fixed magnetic field and a length of wire, how can you increase the induced EMF across the ends of a wire here? So you have a bubbling, just a fixed magnetic field and a length of wire, Basha. So the magnetic field is fixed, but you have a length of wire, okay, inside a magnetic field. How can you induce and bubbling increase the EMF induced, Basha? According to Faraday's law, if you bend that wire into, for example, a certain loop here, because now, of course, in this case, we have n number of turns of wire. Now, once you make a fixed number of turns, the area cannot be changed. Because these are inversely proportional. Cross-sectional area for example, like this one. Cross-sectional area this is one thing. This number of turn an area, you can say these are almost like we cannot change that anymore. Magnetic field the only thing that you can change now it is the time, Basha. Because according to this, EMF the negative n changing AB cosine, Basha, or fixa, you could change two things now. When you got man number time. So how can you increase this, Baba? By decreasing the time, which means that by inserting this coil of wire into the magnetic field very quickly in and out, that increases the EMF induced over there. Basha? Kata, using the wire, I'll make a coil, Basha, with n turns because these are directly proportional. More turn means more EMF. Then move the coil back and forth rapidly, very quickly. That decreases the time which inside bubbling the magnetic field, that increases the EMF induced. Zohar Basha. Now we're going to talk about these study tips, Baba. These are, I can tell you by far, the most important study tips, because if you know these keys, you can answer all the questions that are following regarding this concept. Agar-Anish Nazani might be a little bit difficult to do them, Basha. So let's begin with each one of them. If the coil or the ring is pulled out of the magnetic field or the field is removed, Basha, then the magnetic flux will decrease and it becomes zero. What exactly does this mean here, Basha? If the coil is removed inside a magnetic field, let's say here's a magnetic field, Basha, and here's a coil. If this coil is removed inside a magnetic field, watch this, Baba. If it is removed, or you can say pull out. Magnetic field here, right? So you can call that initial. But what happened once you remove that from a magnetic field, Baba? Once you remove that, there is no magnetic field anymore. So can I say B final or magnetic field second is going to be zero? Because you removed that from a field. There's no field anymore. Agar his field the magnetic field is zero. That is first. What about the second one? What if, for example, you insert this time a coil into a magnetic field? Insert, Basha. Insert or let's say push a coil into a magnetic field. That means previously it was not inside a magnetic field. So we can say B1, B initial is 0. But then after that, you insert that into a magnetic field in here. But now, after it was, for example, after it is pushed into or inserted into magnetic field, got that B final, okay, it is something when yeah, or B second. I got no khalibi. Basha, this is regarding this. Har category, if it is pulled out, yani akhiri magnetic field decay will be 0. If it is inserted, yani was not in the magnetic field, so B initial is 0. Sidi kashmani bab adatan. Whenever it gives you an area, for example, a radius, you can always find area here. Basha, har category this, I find area because that would be the area of a circular loop, which is going to be what? Pi r squared. بس بشارك معنى إذا بدلي a rectangular coil باش أقدر dimension داوية length width داوية أو كات you can find the area by using length times the width. That is for rectangular coil. باشا rectangle length width كمان دبيت نو كاتي. This is how you can find the area. طبعا بلين خالي ترم بابا whenever if the question gave you resistance or if the question is asking for current, always use Ohm's law. باشا use Ohm's law. Ohm's law تسيكاكا لأن resistance دكاتة تسبابة دكاتة EMF volt لسر current باشا. So now you can cross multiply to find whatever that you want. You most of the time you will be required and asked to find the current current دكاتة EMF, the one that you find divided by the resistance, and that's it. باشا. Let's see if there is anything else we can add to these 4 points here. باشا اگر لو keyword بي بابا لخوت underline كان زور استفادة لذكي. That means if the coil or the ring is pulled out أو كاتي يكسر the line pull out B final كان B2 كده بيتسن بابا 0. باشا or the field is removed عينشت. أو زار if the coil or the ring is inserted into or put into أو كاتي B initial لك صفرة B final لك دتوان بلين magnetic كان flux initial صفرة بس B final كمان دبيتين يعني B2 كا there will be a something. باشا تسيدي كشمان هي. If the radius is given, بس يماك بابا area كي بونو عيدا بينيو. أجر بابلين width through length كا given يعني dimension كان given, you can use this one here. Use Ohm's law. تكاتك if R or current is given or required. هر كاتك current داوا كردو resistance داوا كردو بابلين resistance دراوي عن داوا كراوي لقى current. Use Ohm's law. This is one of the questions that we have. Let's solve this one and see how these above points will help us answer this question. يلا بقى pick up سارة حلقة. يلا بسارة تطلع بابا. We have a coil with 25 turns باشا. لك ناخد بنص بابا. This is the number of turns. That is wrapped around a hollow باشا tube with an area of own. The kata area كشي داينة. So number of turn is, let's change this color. Number of turn is 25 باشا turns. Area كمان here it is 1.8 meter squared. 1.8 meter squared باشا. تسيدي كشمانة. Each turn has the same area as the tube on a uniform magnetic field is applied at a right angle to the plane of the coil بابا. كدلية uniform magnetic field is applied at a right angle to a plane of coil يعني flux كمان maximum قاعد ليبي. كدلية at right angle to this يعني cosine gosh okay debit is صفر because if this is the magnetic field direction area k will be parallel to this. So حركاتك بابا in order to induce EMF قاعد ليبي دبي angle كا it has to be at a right angle to the plane to the surface of the bubbling cross-sectional area bubbling to the plane of the loop. باشا قاعد لو خالق بيتم. تسيدي كشمانية. That is for that. So you could write theta 0. I could write shneke, it doesn't matter. If the field increases uniformly from on the Tesla to on the Tesla kata B1 it is 0. Or let's just say 0 Tesla B1, B2 because it increases 0.55 Tesla. These are the two fields in 0.85 second. Got that time 0.85 seconds. What is 85 second. زور باشا. No second. find the magnitude of the induced EMF in the coil. Let's find the magnitude of the induced EMF in the coil. باشا تبى بابا EMF كيف ببينه؟ قلت مان EMF دكاتره negative N قلت مان the beta change in A B cosine theta over delta T. بس استاد شيء قراءة بابا delta B كقراءة ونيا كاتا you can put the other values out of the bracket in here. So EMF دوباره دتواني بلين negative N باشا A cosine theta then هذا دتواني بلين B2 minus B1 divided by delta T, because that is the change in the magnetic field in here. Negative, and كمان سنبو بابا, that is 25 times area it is 1.8 باشا times cosine صفري ما نش نسيو عسايا هر كاتب كواغوتي perpendicular بابا هر ما ينسو باشتره أو كاتب ينسو أجر قوتي أجر قوشكي داوية يعني if it says parallel أجر لي بوكاتي همش تقدر بيتا صفر B2 كمان ده بيتا center is 0. Let's just make this one a bit bigger. 0.55 minus 0. I should divide time it and the 0.85 second. You do the math baba I got leavy. Okay, you get negative what? But mashacha والله making. أو EMF column under is the beta negative 25 volt. Bashkaka. عفوا 29 volt. Basha. This is the EMF that is induced. We can now box a cheese so that you can find easier whenever needed. That is the first part of the question. The second part says if the resistance of the coil is 2.5 ohm, find the magnitude of the induced current. هلا نوتا كان لبيت بابا قلت من هركاتك resistance دراوي يان داوا كرابو use Ohm's law. Kata that would be the second part. قلت من Ohm's law. Let's say you could say resistance the kata EMF لسر current أو the current كيف بينه the current the kata EMF لسر resistance EMF كمان negative 29. Resistance كمان it is 2.5. Let's do the math. You'll get this much current. You get negative 12 amperes. This is the current that you will get. I hope you practice them and you get everything correctly. Easy لخود مشيان إن شاء الله. هرون دي تدا شتي زحمتي تدانه. طبعا دكري ليرة pedal magnetic field that can increase ببابا. وكاتي of course you can tell. How do you tell, for example, if it is increased or not? When the time is 0, magnetic field decay is 0. After the time, for example, passes by 0.8 seconds, you can see that there are magnetic field line increasing. So obviously the magnetic field strength is increasing. This is how you can solve these questions very, very easily. Let's see how other questions can be solved. A single circular loop. Underline كبابا. زور باش. تسمعني single circular loop. كتلا single circular loop يعني single loop يعني جماري أنا كتسمى بابا n is equal to 1 term. تيدي كاش معنى of radius. This time تي دايني بابا radius دايني radius كتسمى 22 centimeter. يلا convert متريكا 0. divide by 100 0.22 meter. باش بس ما area من ديكاك area دكاتا pi r squared أقعد ليبي دكاتا pi times 0.22 square أو كات area كده بينيا زور باشا. In a uniform magnetic يعني بابلين uniform external magnetic field with a strength of own ده باشا كاتا ده 20 بلين بيا كمان سند بابا 0.50 Tesla so that the plane of the coil is perpendicular. But ما كده ليه perpendicular بوشة كتسند الصفرة كاتا cosine صفر the beta 1. The coil is pulled out steadily باشا يعني steadily out. لبيتا قلت مان if it says pulled out يعني تبابي يعني now it is no longer in the uniform in a magnetic field. أو كاتي B2 وكا تيلي the beta الصفر. B initial كان B1 is this much, B2 will be 0 because it's pulled out in 0.25 second. 0.25 second or delta T here. باش كاكا. Find the average induced EMF. باشا. Oops. ضل تبينا بابا. Find the average induced EMF. Oh, what is wrong with this? You're too excited or what? ضل تبينا كاكا. Find the average induced EMF. ليرة باسي كرنت وشتينا كدي تنها إما فكي ببينوتا. Okay, يلا let's get back to the other one. Alright, here باشا average EMF. يلا كاك قلت ماكو EMF أكيد بينا EMF دكاتة negative N شي قورة magnetic field دكا قورة كواتا أي كوساين كي دير بينا باشا دبيتا B2 minus B1 over delta T. Divided the kino, number return account is 1. Don't forget the negative. Negative 1 times area. Come on, send the baba. We don't have, you could just use a calculator to find out. I could not. I'd want to say pi times 0.22 square. Basha. The bawi labam. وهم area كي times cosine صفر. ناش نسي مشكلة times B2 كمان send the baba. قال لي بدل pull that كاتا 0 minus magnetic field دي كم ين? It is 0.5 Tesla divided by the time which is 0.25 second. Do the math. والله ما كده بيني بابا. طبعا قاعد لو negative AB أو do negative بابا دبيته positive something كاتا إيما فكده بيته سنت دبيته 0.30 أو إيش دبيته volt and that is the EMF induced for this question right here. هرون ديت ده. يلا ديكاك هات مشاو برسالنا برساري وزارية دتوانا بلم عينن كوبي بيست زاري بار جمارة كان دقورن زاري بار هيتي لنا قورن أو اللي خود حلقه لو برسارش معنى بابا دتوانا بلم عينن شتا حالي بكيني عن بيوزناكا لو اللي راد الرستانس وشتي داي باشا ضلت سببينا يلا دي بقى حالي كن a coil of wire زور باشا a coil of on the turn بابا so this is number of turn total resistance معناها قال لي بيقول معناها كاتك resistance تبي use Ohm's law cross sectional area كمان هي it is ready بابا you don't have to do that position with it is plane perpendicular to the field قلت معناها كاتا قوتي perpendicular وكاتي وشكل صفر cosine صفر is 1. What is the average current باشا اللي ربنا على EMF ببينه بابا you have to find the EMF first باشا what is the average current is induced باشا in the coil during 0.25 second or delta T that the magnetic field drops بابا from negative 1.6 to 0 the drops قال لي يعني this is initial and this is final here باشا ما دام قلت مان because we have or we're given the resistant the question says find the current man always use Ohm's law or دكاتة سبابة دكاتة EMF لسر current ما current كمان ده the current that is equal to EMF لسر resistance باش كاكا resistance كمان سندا let's just write it here باشا current دكاتة resistance كمان it is 23 ohms the EMF divided by this one yeah by 23 ohms is that EMF كمان هي نيت مان كاكا روبيبي نو أزدو عليه كوشنا كي دابلين ضلن EMF دكاتة negative negative n a cosine theta ضلن B2 minus B1 لسat delta T because the magnetic field is changing كاتا بابا because it asks for the current you need EMF so whether they talk about EMF or not you have to find them so that you could do this زور باش قلت مان إنا كتندا it is negative 205 times area كمان سندا it is 0.25 times cosine كي منوسيا بيزناكا it says drops from on the باش كاتا this becomes أبا قال لي بي أو إن شاء الله أو ديك final الله زورها قال له خالي بي a lot of students for example like do the opposite here باشا كاتا 0 minus 1.6 divided by the time which is 0.25 استوى دبيتا positive EMF فكا positive سنة تماشي كانت 328 volts 328 volt باش كاكا oh voltage كيس now bring this one here into this 328 volt divided by 23 now you can find the current which is 14.3 باشا which is 14.3 لبروي current إيش بأمبير باش كاكا. This is how you can do that. Not easy peasy I guess. زور باشا برسارش تيكش حلكن ضل circular loop باشا مو بزمشت تشوية تدانية حالك بخد حليك أحباب برسارد له حلكم أو برسارة the area is changing here برسارة شجوانا ضل flexible loop باشا كاتا تن loop معناه يعني كويلك جماري أنا كان تن باب جماري ترنا كان just one. It says a flexible loop or a loop. When yeah, kata n, it is only one turn. I got it. Bash. Of conducting wire has a radius of on. But my kata radius derabu baba. Find the area. Area the kata pi r squared. Kata pi times radius command senda. It is 0.12 meter or meter. Just don't forget the square. You can find the area. Bash. What is next? It says perpendicular to uniform magnetic field. Now the angle is 0. With a strength of own, we can say that B it is equal to 0.15 Tesla. It says as in the figure below here, which is shown right here. You can see that. Masha? A. What about part B? You can see. Next says the loop is grasped at opposite ends here. It's the loop here, grasp, bubbling. It is this point here. I just moved that. Is that if this loop, imagine this is elastic band or hair tie, doesn't matter. What happens if you grasp it, if you pull it from both sides here? Of course, this is going to, like the area is going to change. That area will decrease when, that is what the question is saying here. So grasped at opposite ends and stretched until it closes to an area of this much. Now we have another area this time, right? So at this point here, Baba, the area is changing. Because the area is changing, and we already had a radius, that means there are two areas now. MashaAllah. So, good man, now we can call this one the first area. So this is going to be the second area, Baba. Area 1, but it is ready, it is 3 times 10 to the power negative 3 meters squared. That is the second area. So you can see that this question here, the area is changing. MashaAllah. Right. So here's what it is. I believe. All right. So what is it now? The question says, as in figure B below, if it takes 0.2 second to close the loop, yani the time that we have, it is 0.2 seconds. Find the magnitude of the average EMF induced in the loop during this time. Find what? The average EMF induced, kaka. The average EMF induced. Good man, EMF dakat sababa, because the air is changing now, we can say it is negative n or zarababa. B akidini nadere. B cosine, basha, debita say debita area 2 minus area 1 divided by delta t. You can put that in a bracket. Negative, good man, and a kawana, B akatsanda, it is 0.15 Tesla times cosine 0. Good man, area idwam tsanda 3 times 10 to the power negative 3 minus. Be careful once you plug these numbers into a calculator. Basha. Mine is the first area. I think we found it here. That's really odd. But still, the area yakam mandakat it's about 0.045. Basha. 0.045. Ajmar al-Labirbi. So now let's write it down. 0.045. Now divided by delta t. When delta t gets on the good one, it is 0.2 second. Now once you do the math, of course, you can find the answer. EMF akadakata tsand, you could just say EMF dakata 0.032. Masha, but positive is that in volt kak. because this is obviously smaller than this. That's it. There's nothing more than that. يلا بدي بساري ديكا. بسارش مانه بزانم ليرة بس يكين باشا. أواني ديكا بزانم أو بسارنيكا دمينيتو بساري زور آسانا. ليرة فكرتش دي هي بابا Tesla per second because that is the rate of changing. I believe we'll do this inshallah next time. Keep practicing and I'll see you soon inshallah. Assalamu alaikum wa rahmatullah.